continue with our discussions on third order effects. So, towards the end of last class, I said that let's look at a situation where I have two waves coming into the medium at frequencies omega 1 and omega 2. So, the nonlinear polarization, total nonlinear polarization is epsilon 0 chi 3 1 by 8 of E1 e to the power I k1z minus omega 1 t plus complex conjugate plus E2 e to the power I k2z minus omega 2t plus complex conjugate whole cube. So, the two incident waves will now generate a nonlinear polarization, which will which is given by this equation. Now, the nonlinear polarization, we will calculate the nonlinear polarization, and any new frequencies that appear in the nonlinear polarization will try to generate those new frequencies. And so, when I calculate finally the nonlinear polarization, I need to include the electric fields of those waves also. For example, in second harmonic generation, I initially took omega, calculated the nonlinear polarization, and I found that there is nonlinear polarization at 2 omega. And I also found out under what condition the efficiency for generation of 2 omega will be high. So, if I am close to that condition, the total electric field will now consist of omega and 2 omega. So, similarly here, I start with an electric field at input at omega m1 and omega 2. This will lead to certain nonlinear polarization terms. If those nonlinear polarization terms generate new waves at new frequencies, and if that efficiency is significant, then to calculate the nonlinear polarization, I must include those electric fields also finally. So, this is not complete in that sense, exactly like I did for the second order nonlinearity. So, when you expand this term, as I told you yesterday, there is a cubic term. So, you will have terms like mod E1 square into E1, which is the same frequency as omega 1, and that leads to self phase modulation of omega 1 wave. There will be terms like mod E2 square E2, this into this into this. It is a cubic term, so it is a product of 3 terms. So, mod E2 square E2 will give me self phase modulation at omega 2. I will also have E2 into E2 star into E1. That will also be at omega 1, and that leads to cross phase modulation. So, you will have, for example, you have E1 star E1, and this will have a space dependence of the form k1z minus omega 1t. This is self phase modulation. Then you will have E2 star E1, and that will also have k1z minus omega 1t. This is cross phase modulation. E2 star has no time and space dependence, E1 star has no time and space dependence. So, the only space and time dependence comes from the E1 term. So, the propagation of omega 1 wave not only is determined by the electric field at omega 1 because of self phase modulation, it also depends on the electric field at omega 2 because of cross phase modulation. So, the velocity of propagation of the wave at omega 1 can be controlled by another wave at a different frequency. So, I could have, for example, a very low energy wave or low intensity wave at omega 1, and so its self phase modulation is very weak. I could have a very strong wave at omega 2 frequency. So, although this term will be negligible, because E2 is large, there will be a significant contribution to the propagation of E1 wave because of E2 star. So, the velocity of the omega 1 wave can be changed by the intensity at the omega 2 frequency. So I can use this process, for example, to change the phase of the omega 1 wave by switching on and off another wave at another frequency. So if I can change the phase of a wave, I can use that change of phase to go from constructive to destructive interference when I use it as a part of an interferometer. So this process of cross-phase modulation can be used in applications like all optical switching. So I can switch the omega 1 wave from constructive to destructive interference by changing the intensity of light at omega 2 frequency. So I can build an interferometer, say for example a Mach Zehnder interferometer, and I can ensure that the output goes from one to the other depending on the intensity of the omega 2 wave. So this is a very interesting application in all optical switching, but I'm interested in another term here, which is at a different frequency. For example, if I calculate, so let me look at these frequencies. Let me assume omega 1 is here and omega 2 is some frequency here. Now let me look at a term. Can you tell me the nonlinear polarization at a frequency which I call omega 3 is equal to 2 omega 1 minus omega 2. Omega 3 is equal to 2 omega 1 minus omega 2. So what will be the nonlinear polarization term? So 2 omega 1 minus omega 2, which it must have E1, E1, E2 star, and it will have exponential I. Because of E1, I will have a K1. Because of E1, another K1. So 2 K1. E2 star will give me minus K2, Z. And what will be the frequency? This will be omega 3. Because 2 omega 1 minus omega 2, I have defined as omega 3. Actually, if you expand this A plus B plus C plus D whole cube, you get a lot of terms, and I'm just picking up some of those terms. So this term is, of course, there will be another corresponding complex conjugate. And what will be the factor multiplying? A square B, AB square, A square C, all these will have a factor of 3. When you have product of 3 different terms, then you will have a factor of 6. A, B, C will have a factor of 6, B, C, D will have a factor of 6, A square B or A square C or C square D, all of them will have a factor of 3. Okay, so this is the term which I will get, of course, with epsilon 0 chi 3 by 8. But what is interesting here is, what is the frequency now? You see, this is actually omega 1 minus omega 2 minus omega 1. So if I call this delta omega, this is omega 1 minus delta omega. I'm assuming here omega 2 is bigger than omega 1. So this is omega axis. So this omega 3 will be here, equally spaced on the other side. So when I launch a wave at omega 1 and a wave at omega 2, there is nonlinear polarization in the medium at the frequency 2 omega 1 minus omega 2, and this frequency is exactly equally spaced on the other side of omega 1 and omega 2. If omega 2 was here, omega 3 will be here. If omega 2 is here, omega 3 is here. Okay, so it's just a mirror image. Omega 3 is a mirror image of omega 2 around omega 1. Now, suppose I neglect self-phase modulation and cross-phase modulation, then you can see, that means, let me assume that E1 is almost a constant, that's a pump here. So the propagation constant of this wave now, so what is the phase matching condition I will have? This is trying to generate an omega 3 wave. The velocity of this wave, this polarization wave, must be equal to the velocity of the wave at omega 3 frequency. So if I neglect, please remember, normally it may happen that, as you can see here, the omega 3 wave, the velocity of omega 3 wave will depend on intensity at omega 1 because of cross-phase modulation. Note down here, I showed you that the velocity of omega 1 depends on E2 square, mod E2 square. So the velocity of omega 1 depends on the intensity at omega 2. Similarly, the velocity of omega 3 will also depend on the intensity at omega 1 and intensity at omega 2 by cross-phase modulation. And the velocity of omega 1 itself depends on its intensity because of self-phase modulation. So in principle, I need to worry about all this to find out under what condition I will have what is called as phase matching. That means what will be the condition under which I will have significant generation. But let me assume that the intensities of these lights are very low. So this typically happens in a fiber optic communication system where I have a many number of channels going through. Now, these frequencies are defined by the International Telecommunication Union ITU grid. It's called an ITU grid. These frequencies are well-defined frequencies, spaced by 200 gigahertz or 100 gigahertz or something. And so these are well-defined frequencies. So what it implies is, in an optical fiber, I can use these various frequencies for communication at different channels. These are different channels. Like you have in radio transmission, you have different channels, del A, del B, del C, etc., etc. So these are different frequencies. So here also in fiber optic communication, I can use omega 1 for one channel, I can use omega 2 another channel, omega 3 another channel. So at the receiver, if I pick up omega 1, in my receiver, I will hear the signal at omega 1. My receiver can be tuned to receive omega 3 frequency. So I will receive omega 3 frequency. Now, what this implies is, if I'm using these different channels, the presence of light at omega 1 and omega 2 can create problems at omega 3 frequency. Because the propagation of omega 3 now is altered because of E1 and E2. That means the presence of omega 1 and omega 2 frequencies in the communication link can alter the propagation of omega 3 through this effect, and this is called four-way mixing. Mohit.
So you said that the velocity depends on the intensity also.
Yeah, because self-phase modulation. What is self-phase modulation? The refractive index changes, which means the velocity changes. So you see, when suppose these were of high powers, all of them, the velocity at omega 3, the velocity as seen by the omega 3 wave, depends on the intensity at omega 3 because of its self-phase modulation. It depends on the intensity at omega 1 because of cross-phase modulation. It depends on the velocity at omega 2 because of cross-phase modulation. Now, the velocity of omega 1 itself depends on the intensity at omega 1 because of self-phase modulation. So when I look at this process completely, if I assume that these are not low power signals, then I need to worry about all the self-phase modulation terms, all the cross-phase modulation terms.
Together.
Yeah, in calculating this phase matching condition. So I'm not going to discuss that, but I'm going to assume that these signals are low, which means I can forget about self-phase and cross-phase modulation terms. They're not very significantly high. So what will be the phase matching condition? If I neglect XPM and SPM, the phase matching condition implies that the velocity of this wave must be equal to the velocity of the wave at omega 3 frequency. So the omega 3 frequency will have a propagation constant K3. So the phase matching condition will be K3 is equal to 2K1 minus K2. This is neglecting XPM and SPM because I am neglecting any contribution to the Z dependence from E1 and E2 star. Please note that E1 I have written as exponential I omega 1t, K1Z minus omega 1t, but actually K1 will itself gets modified because of self-phase modulation. K1 will get modified because of cross-phase modulation. So all those terms I need to worry about in a complete analysis, but here for low signal values, which is what we will discuss here, the phase matching condition implies that K3 must be equal to 2K1 minus K2. That means it implies omega 3 by C refractive index at omega 3 must be equal to 2 times omega 1 by C refractive index at omega 1 minus omega 2 by C refractive index at omega 2. The propagation constant is the frequency omega by C into the refractive index at that frequency. Yes?
The omega 3 is generated by the nonlinear polarization.
Yeah.
So this K3 that you have written in this expression, what does it stand for? I mean,
So,
it's not an independent wave.
no, the electric field at the omega 3 frequency will be written as half E3 exponential I K3Z minus omega 3. I don't know, let me call it by some other symbol here. This is the velocity. The velocity of the wave at omega 3 frequency is omega 3 by K3. If I neglect the effect of the presence of omega 1 and omega 2 on omega 3 because of cell phase and cross phase modulation. Because otherwise, please note, as I showed you in cell phase modulation or cross phase modulation term, E3 is not, it doesn't propagate like this. It also has a phase change because of the presence of the other signals, which I am neglecting here. The nonlinear polarization has this term. The electric field has this term. So omega 3 by K3 must be equal to omega 3 by 2 K1 minus K2, which is what is this condition. This is very similar to Kp is equal to Ks plus Ki, which I got in the three-way mixing term. The idler propagation constant must be equal to omega Kp minus Ks, which is what I got in the three-way mixing. In the four-way mixing, at this example, it tells me K3 must be equal to 2K1 minus K2. So if I assume, for example, so let me do a simplified analysis. Let me assume this is omega 1, this is omega 2, which is equal to omega 1 plus some delta omega. So omega 3 is equal to omega 1 minus delta omega. So this condition, so let me call delta k. Delta k is equal to 2k1 minus k2 minus k3. Okay, so this is 2 omega 1 by c n at omega 1 minus omega 1 plus delta omega by c n at omega 1 plus delta omega minus omega 1 minus delta omega by c n at omega 1 minus delta omega. Now let me do a simplified analysis from here. So let me write like this. So delta k is equal to 2k1 minus k2 minus k3. So this is equal to 2k1 minus. So okay, let me write like this. 2 times k at omega 1 minus k at omega 1 plus delta omega minus k at omega 1 minus delta omega. Okay, so this is 2k at omega 1 minus, let me make a Taylor series expansion, k at omega 1 plus delta omega dk by d omega at omega 1 plus delta omega square by 2 d square k by d omega square at omega 1 minus k at omega 1 minus delta omega dk by d omega at omega 1 plus delta omega square by 2 d square k by d omega square at omega 1. If delta omega is small compared to omega, omega is of the order of 10 to the power 15 hertz, second inverse, radians per second. So if delta omega is 10 to the power 10 or 10 to the power 9, then delta omega is small compared to omega, and I can make a Taylor series expansion. And as you can see here, this plus this cancels off with this, and this cancels off. So I will essentially land up with minus delta omega square all I'm trying to find out is how does delta k depend on the frequency difference delta omega under the condition that delta omega is small compared to omega. So delta k is proportional to the second differential of k with respect to omega. This quantity is termed group velocity dispersion. Second differential of k with respect to omega is actually depends on, it's effectively proportional to the second differential of refractive index with frequency or wavelength. This is related to dispersion. So if I want this process to be efficient, this must be 0. And a medium which possesses this property medium will possess this property at some frequency or a wavelength, and that frequency or wavelength is called the zero dispersion wavelength or zero dispersion frequency. For example, silica, if you take silica glass, it has this equal to 0 around 1.27 micrometers. 1270 nanometers, this is 0 because of the way refractive index varies. Actually, if you plot refractive index versus wavelength, it will go like this. And in fact, this term d square k by d omega square is proportional. So let me, I'll leave this to you to calculate. So d square k by d omega square is actually lambda q by 2 pi c square Please use expression for k in terms of omega or wavelength and refractive index and convert this differential from omega to lambda. You know the relationship between omega and lambda, you know the relationship between k and refractive index, so you just need to change the differential from d square k by d omega square to d square n by d lambda square. So you see here dn by d lambda is negative, and as you come like this, it decreases, and then it starts to increase again, the first differential. This second differential will be 0 here, but the curvature changes from positive to negative. So this is the wavelength. Around this wavelength, you will have d square n by d lambda square as 0 or d square k by d omega square as 0. And that, as I said, for silica material, it's about 1.27 microns. For different materials, it may be different. It will be different. And so, if you want to use silica and achieve good four-way mixing, you must be close to this wavelength of 1.27 micron. Now, in optical fibers, it is not k, but the propagation constant of the mode that is propagating through the fiber, and this condition actually it gets a little more modified, and by choosing fibers of different diameters and different refractive index profiles, you can move this point elsewhere. So if you want good four-way mixing at a different wavelength, say 1550 nanometers, you can shift this position of this inflection point to a 1550 nanometer wavelength by designing an optical fiber. Because when you take an optical fiber and light propagates through the medium, it not only depends on the medium refractive index, but also on the geometry. If you have studied metallic waveguides, the velocity depends on the dimensions of the waveguide. Similarly here, the velocity of the waves depend on the dimensions of the waveguide of the fiber, which means k depends on the dimensions of the fiber. K1, K2, K3 are all dependent on the materials as well as the geometry of the fiber. So by appropriately designing, it is possible to shift this wavelength of zero dispersion to other wavelengths, and so I can actually achieve a good efficiency for this process of four-way mixing. If I don't want four-way mixing, I can ensure that this is not 0. In communication systems, I don't want crosstalk. I don't want that signals carrying information at these two frequencies, signals carrying information at these two frequencies should alter anything to do with at omega 3 frequency. So I would operate at a wavelength at which this is not 0, close to 0. Then this four-way mixing is very much reduced. So depending on this parameter, I can have large four-way mixing, high efficiency four-way mixing, or I can decrease the four-way mixing efficiency by an appropriate choice of the wavelength of operation, or in optical fibers by an appropriate choice of the geometry of the optical fiber. So we will not discuss these here, but this is a very important aspect in the field of optical fiber communication, because this particular four-way mixing causes problems in distorting the signals at other wavelengths. It leads to crosstalk. Okay. There are other interesting things that can happen here. For example, this is also used for converting signals at one wavelength to the same signals at another wavelength. So for example, if I have signals at omega 2 frequency, I can mix this with another wave at omega 1, and I will get the same signal at now omega 3 frequency. These are called wavelength converters. So I have some signal. Some signal means I have a sequence of pulses coming at omega 2 frequency, and I want these pulses to shift to another frequency or another wavelength. So what I can do is I can mix these signals with another wave such that this omega 2 waves get converted to omega 3 wave. These are called wavelength converters, and in applications like routing of optical signals in optical networks, this is a very important component. These are called wavelength converters. So this is another application, and for this obviously I need to choose the fiber to have high four-way mixing efficiency. Okay. So as you can see this process, what is this process? If I write it slightly differently, this process is satisfying this condition. So 2 omega 1 is equal to omega 2 plus omega 3. This is the same equation I'm writing in a slightly different fashion. This is omega 1, this is omega 2. Now, if I want to solve the problem of how does the electric field at omega 1, omega 2 and omega 3 vary with propagation, how would I solve? I will find out the nonlinear polarization at the three frequencies. I will substitute in the wave equation. I will use the same procedure that we had used to obtain equations for omega s, omega p and omega I for the three-way mixing process. Here I will have three equations, one for omega 1, one for omega 2 and one for omega 3. The conditions now is 2 omega 1 is equal to omega 2 plus omega 3. There it was omega p is equal to omega s plus omega I. So I will not go into details, but you can show that this process can lead to amplification of the signal at omega 2, exactly like the amplification of omega s by omega p. In a three-way mixing process, I can amplify the omega 2 signal. When I generate omega 3, I will also amplify omega 2. Because what is this process? It is two photons at omega 1 frequency splitting together into one photon at omega 2 and one photon at omega 3 frequency. So every time I generate omega 3, I will have to generate omega 2 also. So omega 2 will automatically get amplified as it propagates through and as it generates omega 3. So this is called again an optical parametric amplifier, and this uses chi-3 nonlinearity. And this amplifier based on optical fibers, because you have optical fibers in which you can have a long distance propagation, and this is called a fiber optic parametric amplifier. Or FOPA. Fiber optical parametric amplifier, this is a very important component again, And there is a lot of research going on in achieving high efficiency amplifiers, broadband amplifiers, and so on using this process. This is the Chi3 process compared to Chi2 process for crystals. And this will happen in all media. For this, of course, I need to satisfy the conditions for phase matching. Okay, now, so to obtain the gain coefficient and all those things, I need to solve all the three equations. I do the similar kind of approximations, maybe pump depletion, neglect pump depletion, which means usually this is the pump. So this is the pump, which is called omega p. I can call this omega s and omega I. So this equation is 2 omega p is equal to omega s plus omega I. There it is omega p is equal to omega s plus omega I. So it's a 4-wave mixing because there are 4 frequencies which are interacting in this equation. Omega 1 plus omega 1 is equal to omega 2 plus omega 3. There it was 3-wave mixing, here it's 4-wave mixing. So again, we will not solve these equations, but you got enough basics here to sort of use this analysis and parallel analysis to what we did for Chi2 process to analyze the problem of fiber optic parametric amplifier. Also, if I take a medium and launch only omega p, classical equations do not predict the generation of the signal and idler pairs. But I will find generation of omega s and omega I simultaneously coming out, satisfying this equation, satisfying the equation 2 omega p is equal to omega s plus omega I. Of course, provided I satisfy 2 kp is equal to ks plus ki. So again, this is a process in which I can spontaneously generate pairs of photons at symmetrically located around the pump frequency, one higher, one lower. In that case, it was both were lower frequencies. In the 3-wave mixing case, omega p is equal to omega s plus omega I. So omega p will generate 2 photons at 2 lower frequencies. Here, waves at omega 1, omega p will generate 1 at a slightly higher frequency and equal 1 at a slightly lower frequency, exactly situated on the other side. And so, just like the photon generated in that process, this is also an interesting way to generate photon pairs and do experiments in quantum information or quantum communication and so on. So again, this is a lot of interesting physics in this area. What we will do in the class later on as we go through quantum mechanics is solve the problem or look at the problem of Chi2 nonlinearity and the photons generated in that process, and we will not consider this in the class. So this is also an interesting aspect to this 4-wave mixing process. In fact, you can further generalize from 2 input waves to 3 input waves, and you will find all kinds of frequencies and so on. Okay, so we will not continue with that. Okay, so with that, I want to finish the 4-wave mixing problem, and before we start the quantum aspects, I want to just briefly discuss one more very interesting aspect of this Chi3 process. Okay, before that, do you have any questions? Okay, what I'm going to discuss is what is called as optical phase conjugation. I'll briefly discuss this as an interesting example of Chi3 nonlinearity. Now, all the time we have been discussing, we have assumed that all waves are traveling in the same direction, collinear. But it's not required, because I can have waves going in different directions, total electric field I calculate, and I calculate the nonlinear polarization and so on. So in phase conjugation, I'm going to discuss an example in which the waves are not propagating in the same direction, but maybe in different directions. And the phase matching conditions now become vector equations rather than scalar equations. So what you had as Kp is equal to Ks plus Ki will become Kp vector is equal to Ks vector plus Ki vector. Similarly, this will be 2 Kp vector is equal to Ks vector plus Ki vector. They'll all be vector equations. We could write the scalar equations earlier because we assumed that all the waves were propagating in the same direction. So the vectors, they're all parallel, so it just becomes a scalar equation. Okay, now before I discuss this problem, let me look at the following problem. Suppose I take a mirror. Okay, if I take a normal mirror and I send a wave like this wave goes here. Suppose I had a different mirror in which if I send a wave like this, it comes back. No matter which direction I input. So I have another wave coming from here, it goes back. Here is a wave, this goes back. Here, if I send this wave, it will go here. So, I mean, obviously in the normal mirror, the reflection is, the reflected wave is not going back towards the incident wave. This is the normal mirror. This is a phase conjugate mirror. It's phase conjugate because a wave going like this is reflected into a wave going backwards. It retraces its path in the reverse direction. Now, imagine a mirror like this, and if you look at this mirror, what do you see? Can I see myself? What will I see? The waves from here will not reach my eye. They will go back here. The waves from here will go back here. My right eye will see the right eye. The left eye will see the left eye. Because light from here goes and comes back. Light from here doesn't go, it goes back here. I can't see that. It's a very strange mirror. Okay, just imagine, the phase conjugate mirror is very strange because it reflects a wave exactly in the reverse direction. So if you had, for example, again a normal mirror, if you had a point source here, this wave would have got reflected and you'll see a virtual image here. In this phase conjugate mirror, it goes like this and comes back. This wave will go reflect here, this ray will reflect here, so you'll form a virtual image. This diverging wave further diverges after reflection. This diverging wave will become a converging wave on reflection. And it retraces its path exactly. So, if you play the reflected wave here on a movie, it will be exactly a time reversed forward wave. The wave started like this, went like this, and so if I play the reflected wave, it will go back to the starting point. So it's like time reversal. It's not time, I'm not reversing time. But what is actually happening is the wave is propagating as if the time has got reversed. A diverging wave becomes a converging wave after reflection. Now this is a very interesting mirror because this can be used for primarily one of the major applications is in overcoming distortions of light waves as they propagate through distorting media. For example, the atmosphere has a lot of distortions because of temperature fluctuations and refractive index variations of air. So the images of stars and the images of various astronomical objects I see is not very clear. The twinkling of the star is primarily because of fluctuations. I could use a phase conjugate mirror to cancel this fluctuation. And I could use this to image an object lying on the other side of a distorting surface, for example, or something like that. So it's a very, very interesting area of application, and this uses the Contd nonlinearity. Now, one of them. There are many other different techniques. Now, let me tell you what the process is. Suppose I take a medium. Okay, I launch a wave like this, and I launch another wave like this. So both of them have same frequency omega. So let me call this E1 and let me call this E2. And let me now launch a wave E3 from here. And also, let me assume all of them have the same frequency. Okay, so let me write E1 is equal to half of, let me write this curly so that I just differentiate. This is E1 e to the power I K1 dot R minus omega t plus complex conjugate. K1 vector is the propagation direction of the E1 wave. So this K1 vector. So K1 vector is here. What is E2? The second wave is half E2 e to the power I. So K2. So this is K2 minus K1. And this is K1. So this is minus K1 dot R minus omega t. And I have a third wave, which is E3, is equal to half E3 e to the power I kz minus omega t. Okay. Now, the nonlinear polarization will be epsilon 0 chi 3 into sum of these three terms whole cube. Right? The total electric field is now consisting of all the three. So, I am writing scalar equations forgetting about polarization states. So, the total electric field is E1 plus E2 plus E3. So, the nonlinear polarization is epsilon 0 chi 3 into E1 plus E2 plus E3 whole cube. Now, among the many terms, there will be one term looking like this. So, you will have, for example, E1, E2, E1, E2, E3 star, this into star of this. So, you will have terms like this cube, this cube, this cube, this square into this, all kinds of terms will be there. So, one of the terms, let me pick it up. This is this into this star. What will be the term? So, there will be nonlinear polarization at the following dependence, which will be E2, E3, sorry, E1, E2, E3 star. Now, what about the exponentials? So, this into this will cancel, and this star will give me minus kz. And then what about time dependence? So, I will have actually, there will be a factor of 6, so, and then of course, there will be epsilon 0 chi 3 by 8, which is appearing because of the half. This half, there will be a cube of this, so it will be 1 by 8, and there is an epsilon 0 chi 3. So, this is the term, there will be a nonlinear polarization term, which will have this as one of the terms. Plus, of course, its complex conjugate. So, this multiplied by epsilon 0 chi 3 by 8. What is this term? This is a wave at the same frequency, but propagating in the negative z direction. And this was z. This is positive z. This is called, this wave, this will try to generate a wave going in the minus z direction, and because the frequency and the propagation constant are this, it is phase matched. The frequency omega has a propagation constant k in this medium, and so the polarization that it generates at the frequency omega but reverse direction is also k, propagation constant. So, this wave is automatically phase matched in the interaction process, and so this polarization term will lead to a wave going in the reverse direction. This is called the phase conjugate wave, and as you can see here, the only difference is the space variation, space dependence has been changed from plus kz to minus kz. The time variation is still minus omega t. So there's an I factor, sorry. The time variation is still minus omega t. What has happened is the exponential plus ikz term has been changed to minus ikz term. So if you shine two laser beams like this into a medium and send a wave from here, this nonlinear polarization will generate a wave in the reverse direction, exactly a replica of E3, but in the reverse direction. Yeah.
The E1 and E2 are strong waves or weak?
Strong. E1 and E2 are supposed to be the strong waves, so that this polarization is having enough strength. Otherwise, the polarization term will be very weak and there will not be sufficient generation. So I should make E1 and E2 to be strong waves if I want this to be a mirror. So this is a mirror which is an active mirror. So I have these waves coming in, and if I send a weak wave from here, it gets reflected and goes back towards the source again, exactly back. Now, please note that any wave can be written as a superposition of plane waves propagating in different directions. Have you done this somewhere in the course? Any time dependent function can be written as a superposition of various frequencies by a Fourier transform. Any xyz dependent wave can be written as a superposition of plane waves going in different directions. So if each plane wave has its phase conjugate generated by the mirror, the entire wave when it goes will generate its own phase conjugate, and that is why I drew that if I had a spherical wave, a spherical diverging wave hitting this mirror, after reflection it becomes a converging spherical wave. In a normal mirror, a diverging spherical wave remains a diverging spherical wave after reflection. That's a very interesting mirror, which is a phase conjugate mirror, and what I will do is next class I will just give you a very short description of a couple of equations of this process, and I'll show you some interesting features of this phase conjugation problem.
Sure.
Yeah.
Here we have two lasers, E1 and E2.
Yeah.
Does the direction of as to where I orient the k vector have any significance?
No, as long as they're exactly opposite each other, because then I need to cancel these. That's all. K1 doesn't come into picture at all finally. So what I can do is send a beam from here, put a mirror here. Okay, so the beam goes and reflects and exactly comes back. That's a normal mirror. So I will have this will. So what is happening is these four waves are exchanging energy in this process. So what is?
What is the direction in which this energy exchange is optimized because of the non-linearity of the crystal?
No, it's automatically phase matched. I need to make sure. I need to consider polarization states. I need to calculate the chi I j k l, which I have not done here. Okay, so I need to do all the tensor analysis there, but this process will be reasonably efficient, and it's efficient. It's an efficient process.
But to optimize meaning to use the chi matrix and use the maximum term from the chi matrix.
Also chi matrix and also overlap. The beams should overlap significantly. See, if I come like this, for example, the volume of interaction is only so much. But if I come at a larger angle, maybe the volume of interaction increases. So I need to worry about those things to make the process of generation of the conjugate wave more efficient. And plus the medium's chi tensor that is available to me in the medium. So next class what I will do is very briefly write down a couple of equations and show you this process. And it's a very interesting mirror. People have tried to use this mirror as a mirror in a laser. I can make a laser out of a normal mirror and a phase conjugate mirror. So any distortions inside the laser cavity gets cancelled because of the phase conjugate mirror. Yeah.
Sir, in this kind of a mirror, the intensity of E psi that's coming out.
Yeah.
Would it be what would be the?
We'll write this equation, then I'll tell you. Yeah. I have to write the coupled equations now. What I must do is write the coupled equations for E3 and E4, forgetting about the depletion of E1 and E2. So E3 and E4 get coupled because of E1 and E2. Okay, see, E4 gets generated by E3, but E4 will generate E3. Because E4 is a wave going like this, it will generate its phase conjugate, which is this direction. So that's the coupling mechanism that is taking
E4
place.
will interact with E1 and E2 to generate
Yes, yes. So that's coupling. So E3 interacts with E1, E2 to generate E4, E4 interacts with E1, E2 to generate E3. And so that gets mixed. And I will have a couple of set of equations. It's a very simple equations which you will solve, and I'll show you some interesting features. Okay. Any questions? Okay, thank you.